Alright, so hi everybody. Uh, we'll be uh, we'll be working in this paper. This is a physical science paper that we'll be working on. And so I'll basically just be going through the methods and the ideas behind solving these problems. Okay, so the paper that we will be working on is coming from the Department of Education, and okay, so the paper that we're working on is coming from the Department of Education. Okay, so the paper that we're working on is coming from the Department of Education. Alright. Okay, so here's your paper, and so we'll be working on the multiple choice questions. Okay, this is part 1 of the video for the 2015 paper. I do plan on trying to complete as much of it as possible, but if not, we will continue a part 2 of the same video for the 2015 departmental paper. So as you can see, question 1 asks us, okay, question 1 asks us, okay, so question 1.1, how would we go about addressing question 1.1? So question 1.1 asks us, question 1.1 asks us about vectors p and q. Okay, in actual fact, it asks us about vectors. So the question is, vector p and vector negative p are acting on a common point O, and the angle between the two vectors is, and so now this is a multiple choice problem. We have to choose between A, B, C, and D. Now the correct answer here, the correct answer is 0 degrees, which is A. Okay, and I'll go through the logic with it regarding the reason why it's A. So for 1.1, it's A because a force is acting on an object. Okay, the object is, let us consider an object A. Okay, let us consider this object and let us call it A. If a force acts on this object, which is P, in any direction, okay, if this is a force P acting in any direction, let us consider horizontal direction, then we know that if a force, if we have a force P, if F, okay, as a vector, okay, if the force, okay, which is a vector quantity, is equivalent to P, then if we negate the force, if we negate this force, let us call it F1. F1, okay, negated, that is equivalent to negative P, okay, and so that just means that the force is acting in the opposite direction. This is the force diagram. Alternatively, you could just draw a force P, okay, and drawing the force occurring on the same side would also be valid. And in this instance, the forces would cancel out, leaving us with a net force of 0. If this is force, okay, 1, and this is the force, the negation of the force, it will act in the opposite direction. Alright, so this is the reason why the solution for this question would be B. Alright, the second part asks us, it says that the statement below refers to scalars and vectors. So vectors can be added together, but scalars, so the possible, okay, so the question says the statement below refers to scalars and vectors, and now it gives us possible options. Option I, and I, 1, 2, and 3 in Roman numerals. So vectors can be added together, but scalars cannot. So now we have to determine which of these statements are true, which of the above statements are true, by determining which ones are false and then not including the ones which are false. So vectors can be added together, but scalars cannot. We know this is false. If I have a quantity such as speed, you will know that if I add two values, two different speeds together, or two different distances, as distance, okay, is a scalar, I would also get an output of a scalar, which therefore implies that this statement about vectors being the only quantities that can be added together but excluding scalars will be false. So a scalar quantity can be associated with direction. We know that scalar quantities cannot be associated with direction because by definition a vector is associated with direction. A scalar is only associated with magnitude, which means quantity, which means how much of something. Therefore that statement is false, and a vector is always associated with direction. That is true, and in this instance our solution here would be D. Okay, so 3 is the only one that's true. 1.3 says a net force F is applied on an object of mass m kilograms and causes an acceleration of a meters per second, okay, squared. So when the net force F on the same object is doubled, the resulting acceleration will be in meters per second squared. So for this problem, we know that our force, initial force applied, okay, so this is 1.3. We know that our initial force applied will be given a force of F, and it says that, the question says that the object has a mass m, okay, and acceleration a. Now we know that, okay, if I could put it, if I could put it like this, this is Newton's this is Newton's second law of motion. If we call the force, okay, if we just let force be equivalent to force, mass be equivalent to the mass that was given, okay, and acceleration which is equivalent to the acceleration that's given. Then we know by Newton's second law, okay, that the object, okay, so we have force equivalent to mass times acceleration. Okay, so this is how we would go about getting our force, and we know that our acceleration in this instance, if we rearrange the equation, we would get acceleration equivalent to directly proportional to force and inversely proportional to the mass. Now it says that on the same object, so if you can see the question, it says on the same object is the force is doubled. So that means now we're dealing with a force, let's call that force F2, okay, so we have doubled the original force, which was F, okay, so in this instance we have doubled the original force, okay, and we're calling it F2. The mass remains the same, okay, and now we want to know what the outcome will be on the acceleration. So if this was part 1, then part 2 would tell us that our acceleration, okay, so using Newton's second law, okay, if we call this I, okay, so that is the equation. So from I, okay, then we can see that okay, our force is equivalent to mass times acceleration. That's Newton's second law of motion. And now we know that our force in this instance, so it's plug and play, is 2F. Our mass is m, and so all we have to do is just solve for a, our acceleration. That is equivalent to 2F divided by m. Okay, that is our force. But originally we knew okay, that we can say that this is actually 2 times a, and let us call this the new acceleration. Okay, so this is acceleration new. So 2a, since from 1, okay, we knew that acceleration is equivalent to force divided by mass. So this is coming from this section over here, and so the solution, okay, you would see in this instance would be C, right? 2 times the acceleration. So now 1.4 says a person stands on a bathroom scale in a stationary elevator, and the reading on the scale is 490 newtons. When the elevator is in motion, the reading on the scale changes to 470 newtons. So what you need to understand in this portion is that the person's weight, okay, so if I can represent this, the person is standing on a scale, and the force that he's applying on the scale would be downwards, okay, so the force that's pulling him toward the earth is 490 newtons, okay, so that's what the scale is measuring, and according to Newton's second law, there's an equal but opposite force that's applied, so that's negative 490 newtons occurring in the opposite direction, okay, So these two forces, okay, but now the force changes to 470 newtons. So okay, force, because we know that force is equivalent to mass times acceleration, and really what the scale is measuring is really the scale. A scale measures your force. Okay, this is the reason why it's represented in newtons. So since the force is decreased, okay, so force final, okay, is equivalent to 470 newtons, and that tells us that that the person's that it appears as though the force has decreased, and so the only way that the force could have decreased is if the acceleration is occurring, or the direction of motion of the lift, which is the direction of the acceleration, okay, occurs in the same direction as that of which occurs in the direction which is downwards, okay, so downwards, okay, so our direction of motion would be occurring downward. That would be our direction of motion. Okay, so we would be moving downward. Okay, that would cause. Okay, that. Okay, so we would be moving downward in this instance. Okay, so in a sense, the weight on the scale would be reduced. The mass would remain the same, but the mass would remain the same in this instance. Okay, so we know that the direction of motion. Okay, so we know the direction. Okay, so we know the direction of motion occurs downwards, is down. And we also know that in this instance the acceleration continues to occur downward. Why? Because gravity is what's causing the acceleration, and we know that gravity always acts toward the earth. Okay, so for our paper we would see that the correct solution here would be B. Okay, so this question 1.5 asks us about the light. A light ray is refracted, and when it travels from air into water, okay, so which one of the following combinations related to the direction and the speed of the light ray is correct? Okay, so when we say that the speed, we know that the light ray, so there's two mediums, 1.5, okay, there's two mediums in this instance. There's, if we consider the vertical line to be the normal, then if we consider a light ray traveling from any angle in, okay, from that normal theta, it's traveling from medium 1, which is air, to medium 2, which is water. And we know that if we call the refractive index of air N1 and okay, refractive index of air and the refractive index of water, okay, as N2, then we know that the refractive index of water is greater than that of air, or in other words, that means that the amount of bending that occurs when we travel from water or from air to water is greater when the medium enters water. And so we know that automatically this angle should decrease. And so we consider measuring the angle from the normal, okay, up until the incident ray, and then obviously the ray that's traveling through the water. We consider measuring that angle from the normal, and the speed, okay, as we travel. If you travel from a medium of high refractive index or low refractive index to one of higher refractive index, then the speed decreases. So therefore we know that from air to water, okay, the if we say okay, so for speed from air to water, it decreases, and we know that our the angle occurring also from air to water, that will also decrease, okay. And so going back to the paper, we see that in other words, the angle, if I can say, when I say decrease, I mean it moves toward the normal. So for the direction of the refracted ray, we already know that since it's moving toward the normal, then that limits our options now to only 2, because 2 options towards the normal. And then we also know that speed decreases, and so the correct solution for this portion, question 1.5, is A. Now 1.6 says a learner is hiding behind an open door of a room and can hear people talking outside the room, although he cannot see them. And the reason for this is, and now it gives us various options. It says sound has a shorter wavelength than light, so you have to determine the truth. Now we know that sound has a longer wavelength than light, because a sound wave is occurring in the microwave. Okay, a sound wave has a much okay, that would be the electromagnetic spectrum. So let me not confuse the two. But a sound has a much greater wavelength in general than that of a light wave. A light wave in the electromagnetic spectrum occurs in the visible spectrum, which is between 10 to the minus 4 to or it's between 400 nanometers and 700 nanometers. approximately. So we know that A is false. Sound has a longer wavelength than a light wave. As just discussed, sound does have a longer wavelength. Light travels in straight lines, while sound travels only around corners. Now we know that light does travel. Light propagates. Okay, usually we draw it using straight lines to refer to the direction in which light travels, but while sound travels only around corners. Now this is not necessarily true, because light also has a wave particle duality. So we know that light has a wave particle duality, which means that it can function both as a line and or a ray, and it can, or a particle duality can occur both as a particle and it can occur as a wave. Okay, we know that the properties of waves, transverse waves, longitudinal waves, the wave properties from that section of your notes, or the textbook, you should know that light has the same properties as sound does. So it just does not require a medium in which to travel in, but it also functions as a wave, and so this is not necessarily true. So the energy in a sound wave is less than the energy in a light wave. So the energy in a sound wave, okay, is less than the energy, okay, in a light wave. Okay, so okay, that would depend. You need a calculation for that. But the correct solution here logically would be that it would be B. Okay, from the discussions. Okay, the leaves of the electroscope in the diagram below are positively charged. So when an object is brought close to the plate, the leaves diverge more, and therefore we can conclude that the object. So in this instance, okay, so in this instance we know that the object is positively charged, and the reason for that should be that the plate is negatively charged. So if the plate were negatively charged, or no, it's positively charged. If the plate were positively charged, we know that light charges repel each other, and so this is the reason why in the electroscope below we see that there's a repulsion occurring between the repulsion occurring between the leaves. Okay, and so if a negative charge were or an object which was negatively charged were brought toward the plate, it would cause the leaves to it would cause the spacing between the leaves to decrease. So this is the reason why we say that if you bring more positive charge toward the plate, repulsion will be and if you bring it close to the plate, the repulsion will be very strong, and that will cause the leaves to diverge more. So the correct answer here is A. Okay. 1.8, it says two charged objects repel each other with a force F when they are separated by a distance D, and the distance between the charge is reduced to 1/3 the distance, and then the new force in terms of F will now be Okay, so the information, what you should be looking at, what you should be looking for here would be that we have a force F, okay, and the two charged objects. So when we're referring to charged objects, you should be thinking of um, Coulomb's law. So with the force F and they're separated by a distance d. So this is the initial information. So if now we reduce the distance, okay, to 1/3 d. So this is what it would look like. We have a force F, okay, initially F. Don't forget um, um, to represent that we're referring to a force, because we use the bar above the force to refer to the fact that this is how we represent. So force is a vector, okay, is a vector. So this is how we represent vectors. We also know that you might have a magnitude of force, okay, and in this instance I would use bars, and so in this instance this is equivalent to just saying F without the bar, okay. So we know from the information given, okay, so we've been given some information, okay, that information tells us that the force, okay, so we have two charged objects, okay, which repel each other. So we since they say two charged objects and they haven't given us the mass, let us assume that the object 1, okay, the mass of object 1 is equivalent to m, and the mass of object 2 is the same as object 1, okay, so their masses are basically equivalent and they're the same object. So now the original distance d, okay, separation, okay, that was just d, and we know, okay, equation, okay, so the equation here for Coulomb, okay, Coulomb repulsion, okay, I mean not Coulomb repulsion, but for the force for two charged objects, okay, m1 m2 divided by the separation distance squared. So in this instance we know that if we just plug this in directly, all the information we have, this is basically our first equation. But now we know, okay, that the second set of information, so this is our information given, okay, our second set of information given, okay, was that the object, so the masses remain the same, but the only difference is that the separation distance now changes. The separation distance now becomes 1/3 the original distance d. So as you can see, it's 1/3 d. So applying the original law or Coulomb's law, now our second equation, our force now becomes km squared, and this was to the power of 2, okay, 1/3 d to the power of 2, but we know that just applying some simplification here, this becomes, so the power of 2, 1/3 9 km squared, okay, which in other words means that it's 9 times the original force, because we know from equation 1 that the force is represented in terms of km to the power of 2 divided by d, and so from this result we would see that the correct solution here would be in fact D. Alright, I'm going to move on to question 1.10. Which one of the following best represents the relationship between current and the potential difference for a conductor which obeys Ohm's law? Ohm's law tells us that for an omniconductor, okay, an omniconductor is one which obeys Ohm's law. So that means that the resistance increases linearly as the voltage and current increase. So from judging from an omniconductor, we'd see that the correct solution here would be the linear graph, and this relationship is directly proportional. So this is basically coming directly from the book, and so the correct solution here would be T for 1.10. Okay, so question 2. We have 3 forces. Okay, so we have forces P, Q, and R of 500 newtons, 200 newtons, and 300 newtons respectively, that which act on a point O as shown in the diagram, and the forces are not drawn to scale. So P, Q, and R. So it says refer to the information given in the diagram above and give a reason why the forces are classified as vectors P, Q, and R. So we know that from the definition of a vector tells us that it's a quantity that has both magnitude meaning how much, and direction. Okay, so in this instance we know vectors are represented by arrows. Okay, and these arrows in this diagram, they have values. So Q is equivalent to 200 newtons, P equivalent to 500 newtons, R equivalent to 300 newtons. Since they have a direction occurring, so we see that for example Q has an angle of 30 degrees with respect to the x-axis, okay, and the terminal arm, okay, Q. Then we know that this quantity Q is a vector, and so similarly we can rationalize the same judgment for P and Q. So determine the magnitude and direction of the resultant force either by calculation or by accurate construction and measurement. Okay, so in this instance, okay, so in this instance, okay, we know that, okay, the forces are not drawn to scale, okay, so also question 2.2 tells us to use a scale, so we can use that scale, 10 millimeters equivalent to 50 newtons, as I represented on the paper. So necessarily there's 2 methods to solve this. So method 1, we'd use an algebraic approach, So by using an algebraic approach, we have to split Q into components, and we have to split P into components, and we have to split R into components. And so we know that sine theta is equivalent to y divided by r, cosine theta equivalent to x divided by r, where r is the radius. Okay, and so when solving for the component of y, okay, then r sine of theta, and when solving for the component of x, okay, r cosine theta. So in general, you would use the following. You would use the following equality. Okay, or these are equal now. Okay, so for P, okay, what do we know? Or let us say Q. Let us start with Q. So we know that R equivalent to 200 newtons. Okay, so in this instance, y then is equivalent to 200, and now we need to know the angle as well. So our angle, let us call that theta for Q, is equivalent to 30 degrees. So sine 30 degrees, and that is equivalent to we'll have to find an angle for sine 30 degrees. Okay, we can use, in this instance we can use special angles. So if you consider the triangle, the right angle triangle, okay, so we know this is 60 degrees, we know this angle is 30 degrees for special triangle. Okay, so 2 and 3, and in this instance we're looking for sine. So sine is always opposite over hypotenuse, and so this is equivalent to saying 1/2 times 200. Okay, that is just equivalent to 100. Okay, in this instance, don't forget that we're working with the newtons. Okay, so that would be the component of y. The component of x is again r cosine theta, which is 200 times cosine 30 degrees. We know that cosine 30 degrees, okay, so it's just the root of 3 over 2 from the special angles. Okay, so I'll just leave it in this form. That's newtons, and so we'd apply similarly the result for P. Okay, so we know P is 500 newtons, and the angle, okay, so this angle that we want should necessarily occur from the positive x-axis and be rotated in a clockwise, counterclockwise direction. So the original angle was 10 degrees, but we'll use the angle from the positive x-axis, so from the terminal, from the initial side up until the terminal arm of 80 degrees. Okay, because one quadrant is 90 degrees. So our angle in this instance that we'll use is 80 degrees. And so just applying the same concept for y and for x, we have 500. So we have 500 sine 80 degrees, cosine 80 degrees. Okay, that will give you a result in newtons. And similarly for r, okay, again we want the angle to occur from the initial arm up until the terminal arm. Okay, so it's one full it's half a revolution plus 60 degrees. Okay, so our angle in this instance would be 240 degrees. So our angle is 240 degrees, and our initial value, the magnitude of the force, is 300 newtons. Okay, so this is a radial arm. The radial arm for R is given as 300 newtons. And now again we know that we just find the components in the y in the x direction, and so we would get okay, we get an output, okay, in terms of newtons. And now okay, and now remember, I've chosen to represent y and x as it would basically occur as coordinate pairs, and but remember that the final magnitude and the direction. So in this case, the way that I've represented is just fine, because for example for y and for x we're only referring to magnitude, but in this instance we haven't calculated the direction as of yet. So we know, so just in general, if I can say that the force, the magnitude of the force, okay, net is equivalent to that would be equivalent to the force, okay, occurring in the direction of q, okay, plus p plus force of q, force of p plus the force of r. Okay, so just one magnitude. I could also represent it similarly, f plus p plus r, and then that would just be the components that we calculated now. So we know that that would be r, no, it would be y of q. Okay, so okay, this would be okay, so we have a resultant. Okay, but we want to first sum the components in the x direction. So I would say force occurring, let's say first start with our x direction. So x of p, or x of q plus x of p plus x of r. And similarly, that would give you a result of saying 200 cosine 30 degrees, okay, plus 500 cosine 80 degrees, plus 300 cosine 240 degrees. All of it, the unit would be newtons, and so if I had to sum that up, I would get, or I should get, 110.3 newtons for the force occurring in the x direction. And now I have to consider the forces. Let us consider the forces in the y direction. Okay, the sum of the forces in the y direction is yq, yp, and y of r. Then the force from what we had calculated would be 200 sine 30 degrees plus 500 sine 80 degrees plus 300 sine 240 degrees. Okay, now final force, the unit there would be newtons, and so if that was now I've made a bit of an error. In actual fact, let me just do it here. We need to consider when summing up the forces. Okay, so we know that our first force occurred. Force occurred at an angle of 30 degrees. Okay, and that was force Q. Force P occurred at an angle which we said was 10 with respect to the positive y-axis, and our final force 60 degrees R occurred at 60 degrees with respect to the negative x-axis. Okay, and now if we had to look at the components of P, just in general, we see that P has an x component, okay, which is x of P, and a y component, y of P. Okay, just in general. For Q has a component also, x of Q and y of Q, and R has a component which is occurring in the opposite direction. So you should take note of the ray that I'm drawing, or the vector, and also the direction of the arrowhead. So in actual fact, R is occurring, the x component is occurring in a direction which is opposite to that of Q and P. In other words, in the negative direction. And so this would mean that if we had to use a graphical description, we'd see that if I had to sum up the components for x of P and for the components occurring along the x-axis for x of P and for x of Q, then we would see that if we had to do it on the same line, but for clarity's sake, I will not, and the vector lengths are not drawn to scale, so this is only a rough representation. But remember, displacement is occurring from, so if we consider this point here as 0. Displacement is whatever is occurring from the 0. And so in this instance, when we consider vector, we're considering this displacement that's occurring. So this change in x after we've summed everything up. And so similarly, if we consider the y components, so y of p and y of q, similarly, we see that if this were also considered to be the origin or the 0 point, then there's two ways you could show this, but you could either show it in this instance. I've chosen to represent them directly on top of each other, but in this instance, a representation which is also occurring as follows. So y of q, y of p, in terms of perhaps a point or a free body diagram, and y of r. Okay, this is just how I chose to represent it, or even as y, okay, of p as I represented the components occurring in the x direction. So now vertically, but now if you just had to consider a vertical representation instead of the horizontal representation, then you would see that from that origin the displacement would be this portion here. Okay, so change in y. So from this analysis, we would see that just to correct what I had originally put forth, our f of x now, so you just have to take note of it, but I would not do everything again, but it would be f, so it would be the x component of p plus the x component of q minus the x component of r, which would give us, again, as I stated, it would give us, okay, so it would give us a final value of 110, okay, 0.3 newtons. Okay, and similarly for the force occurring in the occurring vertically, so we know that it's the component of y of p, y of q minus y of r, because it's occurring opposite to the directions of y of p and y of q. And we also know that if we shift y of p, it will not really affect anything. So we know that then our result, if you did the calculation of adding up 200 or in this instance 500 sine 80 degrees plus 200 sine 30 degrees minus 300 sine 240 degrees, then you would get an output of 332.60 newtons. Okay, so that would be the output in this instance. Now, the force, okay, so that would be your output in this instance. Now, the force resultant, so now you need to note that these components, they are both positive values. And so if we had to look at a diagram on the Cartesian plane, we know that for x component occurring at the origin, that would be moving in a positive x direction, and similarly for the y component. And so we would know that our force resultant, even from the angle theta, should also be lying first of all in the first quadrant. Second of all, we now need to know the resultant force. Okay, so for what we have just calculated are the components. To calculate the resultant, we take, according to Pythagoras theorem, it says x squared plus y squared, and then we take the root. Okay, so in other words, or to represent it in terms of the physical quantities, okay, f of x and f of y that we've used. Okay, so if this were our axis, f of x and f of y, then we would see that it's fy squared plus fx squared. Remember that f of r in this instance is still a magnitude because we have not calculated the direction as of yet. So we just take the components that we've just calculated now, 110 squared plus 332.60 newtons squared. Okay, so I'm not representing the unit at the moment. I will represent that toward the end of the calculation, and if you did that correctly, then the final output would be 350.33 newtons. Okay, and now for the angle, okay, if I can just represent it in this corner here, okay, the angle, we know that from a right angle, we know from SOHCAHTOA that opposite over adjacent, or y over x, and we also know that tan theta is equivalent to the opposite over the adjacent, which is y divided by x. Therefore, theta is the tan inverse of y over x. So in other words, we want the angle when we've been given the function value. And so theta would be tan inverse, and now what did we calculate for y? It would have been, let me go over to the next page. It would have been, okay, it would have been theta, okay, is equivalent to tan inverse, or let me rather put it like this, tan, okay, theta, okay, is equivalent to, for the angle that we're interested in, fy over fx, since we originally said that our we were going to use, we were going to represent our force along the x-axis, okay, and our force along the y-axis, instead of just using general x and y as on a Cartesian plane. So then we can say that the inverse of tan is fy over fx, and we knew that, or we calculated the inverse, we calculated the force, the component of the force occurring in the y direction, and that gave us an output of 332.60 newtons, and we had an output of 110.03 newtons. Okay, and if you did that correctly, then the angle that you should be getting is 71.69 degrees, or if you had to round that to one decimal place, 69.7 degrees, since okay, 9, okay, the last digit that we are removing, which is the 9 in this instance, is greater than 5. Okay, so That is the reason for doing that. Okay. So that is how you calculate that is how you perform the calculation for that is how you calculate the resultant vector. Okay, just in general, that's how you calculate the resultant vector. Now there's an alternative to calculating this quantity by using an accurate sketch, which is the reason why we were given initially we were given a scale which said that 10 millimeters, let 10 millimeters be equivalent to 50 newtons, where this was Q, P, and R. Okay, Q 200 newtons, P 500 newtons, and R 300 newtons. Now, to do this, just consider the following, which will be a rough sketch. I won't draw it accurately, but you would have to make use of a ruler to measure 10 newtons, okay, 10 millimeters, which is equivalent to so 10 millimeters equivalent to 1 centimeter. In other words, for every 50 newtons of force. So in this instance, for example, Q 200 newtons, that would be equivalent to saying, or that would imply that you would be using 4 centimeters, because 200 divided by 4. For P 500 newtons, you would be using 10 centimeters, so this would be the length of your vector. And R 300 newtons, you would be using 300 newtons, you would have a distance of 6 centimeters that you would measure out. So if I can just represent this, so start with an axis. In this instance, I've not physically drawn the axis. I've just shown it as a bunch of dotted lines. And so take any vector. So you could take P, you could take P, Q, or R. But let us start with Q. And so you'd have to draw out from the origin, you'd have to draw out accurately using the correct angle that's given. So that's at 30 degrees. Okay, you draw out Q, measuring the knowing the fact that Q was 4 centimeters, okay, which was 200 newtons. And then from that end point where you end, this is the head to tail method. Okay, so from this point onward, you take your next angle, and we know our next angle is P occurring at 10 degrees to the positive y-axis. Okay, and so in this instance, P was 500 newtons, and so you'd have to draw the arrow accurately using that. And then again, starting from that arrowhead, drawing another set of Cartesian plane axes. you'd then draw in the length with the appropriate angle of 60 degrees, the length of R, which is 6 centimeters. Okay, and so from the theory, it says that from your initial point, okay, so let us call this initial point O, where we started, okay, with our first angle of 30 degrees, draw a line that connects to the final point and with the arrowhead, and if you measure this line, so now you'd have to measure it, okay, it will give you a certain force, let's call that force A in newtons. Okay, so force A in newtons, and it will also give you a specific angle. So if I can just shift this over to this side, we would see that we would get a specific force, we would get a specific distance, okay, or specific force of A newtons, okay, and we would also get an angle if we measure that angle using our protractors from the x-axis, okay, from the positive x-axis, and let's call this angle theta, equivalent to p degrees, okay, and so that would be the result. And we know that if as in the final calculation that we did, from the final calculation that we did, okay, our resultant force, so this would be, or our resultant, the magnitude of our resultant force was 350.33 newtons, and the angle which that occurred at was at 71.7 newtons, and we know that 71, so our angle theta lies between 0 degrees and 90 degrees, and so that we are on the ballpark, in this instance, especially with our diagram. But of course you would have to not show it like this, but you'd actually have to do the measurements yourself. And so this is the result that you would get. And so just to sum up, we could say that the force, now we could use force notation. So for F bar, okay, is 350.33 newtons at you could specify at 71.7 degrees. Okay, so that would be your final result. Okay. Okay. So if I can continue. Okay, so question 3 tells us that there's a force F, and it pulls a 50 kilogram block at a constant speed over a rough surface AB as shown in the diagram below, and the coefficient of kinetic friction between the block and the surface is 0.4. So first of all, he asks us to draw a labeled force diagram. Okay. okay, between points A, okay, and B. Okay, so the block is 50 kilograms. It's moving at a constant speed, and the coefficient of friction between the surface and the block is 0.4. So 3.1 asks us to draw a labeled force diagram. 3.2 asks us to state Newton's second law of motion, and 3.3 asks us to calculate the force F, okay, and 3.4, okay, so we have to draw a free body diagram. Let me just emphasize on that, and not a force diagram. So a force diagram, you would actually draw the block, but for a free body diagram, that's usually represented as a dot. Okay, so I've inputted the information. I've inputted the information here. Okay, so here's our diagram. Okay, and our kinetic friction is 0.4. Okay, the coefficient of our kinetic friction. So the coefficient of our kinetic friction is a dimensionless quantity. So that means it has no unit. Okay, so 3.1 asks us to draw a labeled force diagram. Okay, 3.1 asks us to draw a labeled, free body diagram. And so with any free body diagram, you would know that there's a force. Okay, first of all, there's a force of friction. We know that the object is moving forward, so that force of friction, the force that's pulling the box horizontally, let's call it F of x. That force must be greater than the force due to friction, and especially now we've been given a force due to kinetic friction, and so of course it implies that the object is moving, and that force is greater than the f of x is greater than f of k. Okay, and then we know that for a box that was balanced, so let us assume that the box was balanced, that means that there would be no force occurring in the upward direction, which means that the weight of the box, in other words, the force normal, would be equivalent to the force due to gravity, where they are equal, occurring in equal but opposite directions. But in this instance, we also know that there is a force occurring in the positive y direction. Why? Because this diagram, okay, above, if I can just represent this here, the diagram is split into components, f of x and f of y, and we've got a resultant, which is occurring at an angle of 20 degrees. Okay, so that is one way to represent it. Another way, okay, another way to represent this would just be by drawing the another way to represent this would just be by so considering your point, okay, the force due to gravity, okay, and then the force due to friction, okay, the force, the normal force, the gravitational force, and then just the force that's being applied, okay. So x component and y component, that would also be correct. Now question 2 asks us to question 2 says that we should state Newton's law, first law of motion in words. So for that one, we just know that every object, okay, or it says an object will continue in its state of motion or constant velocity unless acted upon by an unbalanced force. So in other words, if you think of an object in space, that object will continue moving because there's no forces that's acting on the object. There's no force due to friction, and so the object would just continue revolving. Perhaps if we consider the moon or even a comet, just continuing in its direction of motion. The force F. Now it says, what is the force F? And now from our diagram, we know that so we've been asked to calculate the force, okay. So we've been asked to calculate the force F. So we know that force by Newton's law of motion, okay, so we know that force is equivalent to mass okay, so we've been asked to calculate the force F, okay. Okay, so the object is moving at a constant speed, okay, so it implies that it was originally stated constant speed. That means it means that the object has zero acceleration. Even though the object is moving, acceleration is the change in speed. If the speed is constant, if you had to consider a if you had to consider a velocity time curve, okay, so the graphs for position, velocity and displacement, you would see that if you took the derivative of the velocity, or you took the average gradient, okay, so v final minus v initial divided by the change in time, you get the acceleration, which in this instance for t and a, okay, that would just be equivalent to 0 along the axis for any value that you would input when we're considering the positive, when we consider a positive portion of the graph. Okay, so quadrant 1. So in this instance, force is mass times acceleration. We know that the friction the force due to kinetic friction acts in the opposite direction. Okay. So force, okay, is, so doing the calculation, force equivalent to 0 because the acceleration is equivalent to 0. That is just like saying m times 0 is equivalent to 0. Okay, for whatever mass the object might have. In this instance, the mass is 50 kilograms. Then we just say that the force is, so we know that the force is the force that's being applied to the crate or the box is the force that we're interested is the one that's occurring in the horizontal, along the horizontal direction, okay, or the horizontal x-axis at an angle of, so it would be cosine theta, okay, at an angle of 20 degrees, minus the force due to friction, which is a result of the normal force, where the normal force is the force, okay, so in this instance, it would be minus the force due to friction, okay, okay, and so minus the force due to friction, okay, and so perhaps I don't have enough space here, so I just have to move on to a new page. Okay, so the force, okay, so we said that F cosine 20 degrees minus the force due to friction, okay, kinetic friction, but we know that the force due to kinetic friction is equivalent to mu k times the normal force, okay, but in this instance the normal force, okay, is the difference between the it's the difference between the force due to gravity and so it's the difference between the force due to gravity and the force which is lifting the box upward. Okay, so the force lifting the box upwards so contributes to the normal force of the box being less. Okay, so the full weight of the box will not be in contact, the full weight of the box will not be in contact with the surface, okay, and so our force will be reduced, okay, so our force will be reduced, okay, for our normal force will be reduced in this instance, or no, our normal force in this instance due to the fact, okay, so due to the fact that we're lifting the object, so less of the object is coming in contact with the surface, and so the normal force will appear to be reduced because a small amount of the weight of the object is coming into contact with the surface, if you had to consider a scale, okay, so you're supporting some of the weight instead of the scale taking full weight, okay, so okay, so our force due to gravity in this instance, where are represented as Fg. That was the original weight of the box. So that weight was, if I can do the separate calculation, was Fg, okay, equivalent to, so according to Newton's law, it's 9.8 because of gravity times the weight of the box, which is 50 kilograms, which would give us 490 newtons. So this is still equivalent to 0. Okay, we could substitute some values here if we wanted to, or we could just stay with our variables now, for now, okay, and substitute in later, I suppose. So mu k f g sine 20 degrees. Okay, and so now all we have to do is we just have to pull out the common factor for we have to pull out the common factor, okay, and the quantity that we're interested in is force in this instance, that's being applied to the crate, such that the crate is lifting off the surface of the ground. And so in this instance, what I've done is I've just moved mu k f g to the other side, because that weight, the weight of the box multiplied by the force due to gravity is not a quantity of interest, okay, in this regard, okay, so it will contribute to giving us a final value for it will contribute to giving us a final value for the force which occurred due to the lifting of the box off the surface, okay, or lifting the box, or pulling the box forward at an angle. Okay, so we know our mu k is 0.4, we have 490 newtons for f of g. Our angle is cosine 20 degrees. Our okay, again, the same thing. Our angle is sine 20 degrees, and so if you calculated this correctly, you should get a value of 182.156 newtons for the force. Okay, so yeah, okay, so if that was calculated correctly, that is what you should have received, or the value that should have been obtained for the force. Okay. Okay, so so I think I'm gonna leave it here for now. And so we can continue next time with